According to the National Electrical Code, or NEC, branch circuits must be protected against overcurrent and short-circuit conditions. This protection can be provided by circuit breakers, fuses, or other approved devices. Standard circuit breakers provide both thermal and magnetic protection. Thermal protection responds to prolonged overloads, while magnetic protection responds to short circuits. Fully magnetic circuit breakers provide only magnetic protection, which trips the breaker instantly in the event of a short circuit. They do not provide overcurrent protection. For lighting circuits rated at 120 volts or 277 volts and 20 amps, either standard circuit breakers or fully magnetic circuit breakers can be used. However, the NEC requires branch circuits to be protected for overcurrent conditions. Fully magnetic circuit breakers do not provide this protection. Therefore, panels equipped with fully magnetic breakers do not meet the minimum NEC requirements for branch circuit protection. It is generally recommended to use standard circuit breakers that provide both thermal and magnetic protection for lighting circuits. This ensures both short-circuit and overcurrent protection as required by the NEC. Distribution panels using fully magnetic breakers do not meet the minimum requirements of the NEC for branch circuit protection. Panels equipped with standard circuit breakers that provide both thermal and magnetic protection should be used instead. Let's delve deeper into the specifics. The NEC, in various articles, emphasizes the need for comprehensive protection of electrical circuits. This isn't just about preventing immediate hazards like short circuits, but also about mitigating the risks associated with prolonged overcurrents that can lead to overheating and fire. Now, let's break down the two main types of circuit breakers we're discussing. Firstly, we have the standard circuit breakers, often referred to as thermomagnetic breakers. These are the workhorses of electrical protection. They employ two distinct mechanisms to safeguard circuits. The thermal component consists of a bimetallic strip that heats up when subjected to an overcurrent. As the strip heats, it bends, eventually tripping the breaker and interrupting the circuit. This thermal response is designed to protect against sustained overloads that, while not immediately catastrophic, can cause damage over time. Secondly, the magnetic component provides instantaneous protection against short circuits. It utilizes an electromagnet that trips the breaker when a sudden surge of current occurs, such as when a live wire comes into direct contact with a grounded surface. This magnetic trip is incredibly fast, typically occurring within milliseconds, minimizing the potential for arc flash and other hazardous events. The combination of thermal and magnetic protection makes standard circuit breakers a versatile and reliable choice for a wide range of applications. They address both long-term overload conditions and immediate short-circuit threats. Now let's consider fully magnetic circuit breakers. These devices are designed solely for rapid response to short circuits. They rely exclusively on the magnetic tripping mechanism, foregoing the thermal overload protection offered by standard breakers. While fully magnetic breakers excel at quickly interrupting short circuits, their lack of thermal protection leaves circuits vulnerable to damage from prolonged overcurrents. This is a critical distinction to understand, as overcurrents, even if they don't trigger an immediate trip, can still cause significant harm. For example, a slightly overloaded lighting circuit might not trip a fully magnetic breaker, but the sustained excess current can overheat wires, damage insulation, and potentially ignite nearby materials. This is where the NEC emphasis on comprehensive protection comes into play. The code mandates that branch circuits be protected against both overcurrents and short circuits, recognizing that both types of faults pose distinct risks. Because fully magnetic breakers only address short circuits, they fall short of meeting this requirement. This brings us to the application of these breakers in lighting circuits. Lighting circuits, whether operating at 120 volts or 277 volts, are subject to both overcurrent and short circuit conditions. Overcurrents can occur due to various factors, such as excessive load from too many lights on a single circuit, or a malfunctioning ballast in a fluorescent fixture. Short circuits can result from damaged wiring, loose connections, or accidental contact between conductors. Given these potential hazards, it's imperative that lighting circuits be protected by devices that can address both types of faults. Standard thermal magnetic circuit breakers are well suited for this task. Their thermal component guards against overcurrents, while their magnetic component provides rapid short-circuit protection. In contrast, fully magnetic breakers only offer short-circuit protection, leaving lighting circuits vulnerable to the damaging effects of overcurrents. Therefore, according to the NEC, fully magnetic breakers are not an acceptable substitute for standard thermal magnetic breakers in branch circuit applications where both overcurrent and short-circuit protection are required. It is essential to select circuit breakers that provide comprehensive protection, ensuring the safety and reliability of electrical systems. Let's take a moment to clarify the term overcurrent as it relates to circuit protection. Overcurrent refers to any current exceeding the rated ampacity of a conductor or device. It encompasses both overload currents and short-circuit currents, but it's important to distinguish between the two. Overload currents are typically several times the rated current and are caused by excessive load on a circuit. They are characterized by a gradual increase in current over time, which is why thermal protection is effective in mitigating their effects. Short-circuit currents, on the other hand, are extremely high, often thousands of amps, and occur instantaneously. They are caused by a low resistance path between conductors, such as a direct connection between a live wire and a grounded surface. Magnetic protection is essential for quickly interrupting these high-magnitude fault currents. The NEC requirement for overcurrent protection reflects the understanding that both overload currents and short-circuit currents can pose significant hazards. Overload currents can lead to overheating, insulation damage, and fire, while short-circuit currents can cause arc flash, equipment damage, and severe injury. By mandating protection against both types of faults, the NEC aims to minimize these risks and ensure the safe operation of electrical systems. Now let's discuss some practical recommendations for selecting circuit breakers for lighting circuits. Firstly, always consult the NEC and other applicable standards to ensure compliance with all relevant requirements. Secondly, choose circuit breakers that are appropriately rated for the circuit they are protecting. The breaker's ampacity rating should match the ampacity of the conductors in the circuit, and its interrupting rating should be sufficient to handle the maximum fault current that could occur at that location. Thirdly, consider the specific characteristics of the lighting circuit being protected. For example, circuits with electronic ballast or LED drivers may require circuit breakers with specific characteristics to prevent nuisance tripping. Fourthly, always use listed and labeled circuit breakers from reputable manufacturers. These breakers have been tested and certified to meet industry standards for safety and performance. Fifthly, ensure that circuit breakers are properly installed and maintained. This includes verifying that connections are tight, that breakers are properly labeled, and that they are periodically inspected for signs of damage or deterioration. By following these recommendations, you can help ensure that lighting circuits are adequately protected and that electrical systems operate safely and reliably. Let's now turn our attention to the implications of using fully magnetic breakers in distribution panels. As we've established, fully magnetic breakers only provide short-circuit protection, leaving circuits vulnerable to overcurrents. This can have significant consequences in distribution panels, where multiple branch circuits are fed from a common source. If a branch circuit protected by a fully magnetic breaker experiences an overcurrent, the breaker will not trip, and the overcurrent will continue to flow, potentially affecting other circuits connected to the same panel. This can lead to widespread overheating, equipment damage, and even fire. Furthermore, the lack of overcurrent protection can compromise the integrity of the entire electrical system. If a fault occurs on one circuit, it can propagate to other circuits, causing a cascade of failures. This can result in significant downtime and costly repairs. For these reasons, the NEC strongly discourages the use of fully magnetic breakers in distribution panels where both overcurrent and short-circuit protection are required. Instead, the code recommends the use of standard thermal magnetic breakers that provide comprehensive protection against both types of faults. By using thermal magnetic breakers, you can help ensure the safety and reliability of distribution panels and the electrical systems they serve. Let's delve into some specific examples to illustrate the importance of overcurrent protection in lighting circuits. Firstly, consider a retail store with numerous fluorescent light fixtures. Each fixture contains a ballast, which is a device that regulates the current flow to the lamp. If a ballast malfunctions, it can draw excessive current, creating an overcurrent condition. If the circuit is protected by a standard thermal magnetic breaker, the thermal component will detect the overcurrent and trip the breaker, preventing the ballast from overheating and potentially causing a fire. However, if the circuit is protected by a fully magnetic breaker, the breaker will not trip, and the ballast will continue to draw excessive current, potentially leading to a hazardous situation. Secondly, consider an office building with LED lighting. LED drivers, similar to ballasts, regulate the current flow to the LED. If an LED driver fails, it can also draw excessive current, creating an overcurrent condition. Again, a standard thermal magnetic breaker will provide protection against this overcurrent, while a fully magnetic breaker will not. Thirdly, consider a warehouse with high bay lighting. These fixtures often operate at 277 volts and draw significant current. If a wire becomes loose or a connection fails, it can create an overcurrent condition. A thermal magnetic breaker will detect this overcurrent and trip the breaker, preventing further damage. A fully magnetic breaker, however, will not respond to this overcurrent, leaving the circuit vulnerable to overheating and potential fire. These examples highlight the critical role that overcurrent protection plays in ensuring the safety of lighting circuits. Without adequate overcurrent protection, circuits are vulnerable to overheating, equipment damage, and potential fire hazards. Standard thermal magnetic breakers provide the necessary overcurrent protection, while fully magnetic breakers do not. Therefore, it is essential to use thermal magnetic breakers in lighting circuits to comply with the NEC and ensure the safety of electrical systems. Let's explore the different types of fault currents in greater detail. As mentioned earlier, fault currents can be broadly classified into two categories: firstly, overloads, and secondly, short circuits. Overloads occur when the current demand exceeds the rated capacity of a circuit. This can happen when too many devices are connected to a single circuit, or when a device malfunctions and draws excessive current. Overloads are typically characterized by a gradual increase in current over time. Short circuits, on the other hand, are characterized by a sudden and dramatic increase in current. They occur when there is a low resistance path between conductors, such as when a live wire comes into direct contact with a grounded surface. Short circuits can result in extremely high currents, often thousands of amps, which can cause severe damage in a very short period of time. The type of protection required depends on the type of fault current. Overloads are best addressed by thermal protection, which responds to the gradual increase in temperature caused by the excessive current. Short circuits are best addressed by magnetic protection, which responds to the sudden surge in current. Standard thermal magnetic breakers provide both types of protection, making them a versatile and effective choice for a wide range of applications. Fully magnetic breakers, however, only provide magnetic protection, leaving circuits vulnerable to overloads. This limitation makes them unsuitable for applications where both overload and short circuit protection are required, such as in lighting circuits. Now let's consider the role of fuses in branch circuit protection. Fuses, like circuit breakers, are overcurrent protection devices. They contain a fusible link that melts and opens the circuit when the current exceeds a predetermined level. Fuses come in various types, each with its own characteristics. Some fuses provide both thermal and magnetic protection, while others provide only magnetic protection. Time delay fuses, for example, are designed to withstand temporary overloads without tripping, while still providing protection against short circuits. Current limiting fuses are designed to quickly interrupt high fault currents, limiting the amount of energy that flows into the circuit. The NEC recognizes fuses as an acceptable alternative to circuit breakers for branch circuit protection, provided that they are properly selected and installed. When selecting fuses, it is important to consider the circuit's voltage, current rating, and interrupting rating. The fuse's voltage rating must be equal to or greater than the circuit's voltage. The fuse's current rating must match the ampacity of the conductors in the circuit. The fuse's interrupting rating must be sufficient to handle the maximum fault current that could occur at that location. It is also important to choose fuses that are specifically designed for the application. For example, fuses used in motor circuits may need to have different characteristics than fuses used in lighting circuits. When installing fuses, it is important to ensure that they are properly sized and that they are installed in a suitable enclosure. The enclosure should protect the fuses from damage and prevent accidental contact with live parts. It is also important to label the enclosure to indicate the fuse size and type. Fuses can provide effective overcurrent protection for branch circuits, but it is important to select and install them correctly. Standard thermal magnetic circuit breakers are generally preferred for ease of use and reset capability. Let's delve into the specific NEC articles that address overcurrent protection. The NEC contains numerous articles that pertain to overcurrent protection, but some of the most relevant include firstly Article 240, which covers overcurrent protection in general. This article provides requirements for overcurrent protection devices, including circuit breakers and fuses. It also covers the selection, installation, and location of overcurrent protection devices. Secondly, Article 210, which covers branch circuits. This article provides requirements for branch circuit wiring, overcurrent protection, and outlet devices. It specifies the type of overcurrent protection required for different types of branch circuits. Thirdly, Article 430, which covers motors, motor circuits, and controllers. This article provides requirements for the overcurrent protection of motors and motor circuits. It specifies the types of overcurrent protection required for different types of motors. Fourthly, Article 450, which covers transformers. This article provides requirements for the overcurrent protection of transformers. It specifies the types of overcurrent protection required for different types of transformers. Fifthly, Article 725, which covers Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. This article provides requirements for the overcurrent protection of these types of circuits. These are just a few of the many NEC articles that address overcurrent protection. It is important to consult the NEC and other applicable standards to ensure compliance with all relevant requirements. The NEC is a comprehensive document that provides detailed guidance on all aspects of electrical safety. It is essential for anyone involved in the design, installation, or maintenance of electrical systems to be familiar with the NEC. Let's explore some additional considerations regarding circuit breaker selection and application. Firstly, consider the ambient temperature in which the circuit breaker will be installed. Circuit breakers are sensitive to temperature, and their performance can be affected by extreme temperatures. High ambient temperatures can reduce the breaker's ampacity rating, while low ambient temperatures can increase it. It is important to select circuit breakers that are rated for the ambient temperature in which they will be installed. Secondly, consider the altitude at which the circuit breaker will be installed. Circuit breakers are also sensitive to altitude, and their performance can be affected by high altitudes. High altitudes can reduce the breaker's interrupting rating. It is important to select circuit breakers that are rated for the altitude at which they will be installed. Thirdly, consider the type of load that the circuit breaker will be protecting. Some loads, such as motors and transformers, can generate inrush currents that are much higher than their normal operating currents. It is important to select circuit breakers that are capable of withstanding these inrush currents without tripping. Fourthly, consider the coordination of overcurrent protection devices. In many electrical systems, multiple overcurrent protection devices are connected in series. It is important to coordinate these devices so that the device closest to the fault will trip first, minimizing the impact on the rest of the system. Fifthly, consider the selective coordination of overcurrent protection devices. Selective coordination is a more advanced form of coordination that ensures that only the overcurrent protection device closest to the fault will trip, even under high fault current conditions. This can be achieved by using circuit breakers with different time current characteristics. These are just a few of the many factors to consider when selecting and applying circuit breakers. It is important to consult with a qualified electrical engineer to ensure that the correct circuit breakers are selected for the application, and always adhere to manufacturer's instructions when installing electrical equipment.